In this video, we will have a look at transfer learning that will be applied on image classification. I will first explain what transfer learning is, and then the basics of convolutional neural networks. We will also look into the details behind VGG16, which we will use for transfer learning among several other networks. At the end of this video, I will show a tutorial in Python with Keras and TensorFlow to classify cats and dogs by using transfer learning. If you are not familiar with neural networks and convolutional neural networks, I suggest that you have a look at these videos. This video also shows the basics of Python and how to set up and train a simple neural network. Transfer learning is a machine learning technique that makes use of the knowledge stored in the pre-trained model, which is applied on another similar task. For example, suppose that we have access to a network that has been trained on thousands of images of wolves, tigers, and elephants. We now like to create a network to classify cats and dogs, but we only have access to 200 images, which is too few to train a network from scratch, since this network has learned to recognize wolves and tigers, which look quite similar to cats and dogs. We may reuse this part of the trained network, which has learned to recognize things like eyes, tails, and heads, to our new network, and then simply add an output layer with the same number of output nodes as categories we like to predict. Every connection in a network is associated with a weight. The value of this weight has been optimized so that the network can predict as good as possible. Transfer learning means that we use the values of the weights from the pre-trained network, and then add new layers with trainable weights to fit the new task. These new weights will be optimized to, in this case, classify cats and dogs. If the pre-trained network has been trained on images that look quite different from the images that we like to train on, one usually unfreezes the weights of the pre-trained network so that these are also trainable, and freeze just the weights of the first layers. By unfreezing the weights of the pre-trained network, the network will learn to identify new features in the training data. There is a range of open source networks for image classification that we can use to utilize transfer learning. The networks that are shown here can easily be downloaded if you use Keras and TensorFlow. For example, VGG16 is a very deep network, which has a simple architecture. Most of these pre-trained networks have been trained on the ImageNet dataset, which contains more than 1 million labeled images. The images show objects of 1,000 different categories, such as cars, animals, and plants. There is also a larger dataset referred to as ImageNet 21K. This dataset contains about 14 million images divided into 21,841 classes. This column shows how well the networks have performed on the ImageNet dataset. The accuracy represents how often the images were correctly classified in the test dataset of ImageNet. Although these networks are relatively small, which means that they are faster to train, they still have a relatively high accuracy. EfficientNet v2 is currently one of the best networks to classify images in the ImageNet dataset. The largest variant of this network has reached an accuracy above 87%. It is clear that better types of networks are developed every year. To illustrate how transfer learning works, I will here use the classic network called VGG16. This network has been trained on the ImageNet dataset and can easily be loaded if you use deep learning libraries in Python like Keras and TensorFlow. To fully understand the architecture of VGG16, we first need to know the basics of convolutional neural networks, which I explain in more detail in the following video. To illustrate how a CNN works, I will use the following 10 images, where each image represents a digit and has 25 pixels. The network will be trained to predict which digit that is included in the image. To explain the basics of a CNN, let's have a closer look at the image that represents a 0. Note that an image is just a matrix with numbers. In CNN, one uses a so-called filter, also known as a kernel. In this example, the filter is a 2x2 matrix with some numbers. The numbers used in this filter have been optimized during the training process. The following numbers are therefore optimal for this simple example. The filter is then placed on top of the image where we perform a dot product, which means that we multiply the values in the overlapping elements like this. Then we sum these products and add the value to a so-called feature map. Next, we slide the filter one step to the right. How far we move the filter is referred to as the stride length. Since we move the filter 1 pixel to the right, the stride length is equal to 1. Then we do the same calculations again, and continue until we have moved the filter over the entire image. This procedure is called convolution, which is used to detect local features in the image. Then one applies some activation function on the feature map, such as the ReLU function. The ReLU function takes a value and returns the maximum value between 0 and the value that we plug in. Suppose that we plug in this value here. The maximum value of these two values is simply 1, which means that we do not change this value in the feature map. The ReLU function basically sets all negative values in the feature map to 0 and leaves positive values unchanged. Since we have only positive values in our feature map, the ReLU function does not change any of the values in this example. Next, we may perform pooling. In this example, we use a 2x2 window and use max pooling, which means that we take the maximum value of the 4 numbers in the window and place this number here. Then we move the window to these 4 elements in the feature map and place the corresponding maximum number in the pooled feature map. Since we now move the pooling window 2 steps to the right, the stride length is here equal to 2. Then we move the pooling window 2 steps down, and then 2 steps to the right. Finally, we flatten the pooled feature map into a one-dimensional array, like this. The values in this array are then used as inputs in a fully connected layer. The network will have 10 output nodes, because it is used to predict 10 different digits. Since the image contains a 0, the values of the weights in the network will be optimized so that this output node results in the largest probability, because our image contains a 0. In this example, we used only one filter, but several filters are used when we work with CNNs. Suppose that we would use also a second filter. Using this second filter will result in the following feature map and the following pooled feature map. We then connect the one-dimensional array to 8 nodes instead of just 4 in the fully connected layer. CNNs are usually illustrated with boxes, which means that we start with one image which corresponds to a matrix with numbers. During the convolution, we'll get more matrices, one for each filter. After the pooling, the matrices become smaller. Instead of flatten the pooled feature map into a one-dimensional array, one can instead compute the average value of each entire two-dimensional feature map and use this as input in the fully connected layer. You might wonder what numbers that you should use in your filters. Well, you don't need to worry about that, because just like the weights in the fully connected network, the filters have weights that will be optimized during the training process. The weights are initialized with some random numbers, and during each round of training iteration, the weights are updated to improve the predictions. So, in total, we have 8 weights for the 2 filters, and 80 weights that are associated with the edges between the 8 nodes and the 10 output nodes, as well as 10 bias weights, which gives the network in total 98 weights to tune during the training process. We'll now have a look at how the network deals with color images. A color image is represented by 3 layers, or grids, which usually represent the brightness of red, green, and blue colors. The combination of the numbers in the 3 pixels then gives a certain color. In CNN, we say that we have 3 channels, one for red, green, and blue. Suppose that we would use the following 3-dimensional filter that would move across the 3 channels, like this, where we do the same calculations as we did before, and then sum the calculations from the 3 channels that we plug in into a feature map. Next, we move the filter one step to the right and do the same calculations. Note that one can also include a bias weight in this calculation, so that the network has one additional way to tune. So far, I have just shown how the calculations are done with the filters. But how do the filters identify local features in the image? Well, suppose that we would apply the following filter on the 10 images and that it results in a value of 3 when the filter is applied on a certain position in the image. This value is the one that we plug in into the feature map. A value of 3 with the given weights would mean that the filter has identified the following corner, which is present in the following images. By using also this filter, we can identify this kind of corner, which is present in the following images. So, this image is the only image that includes 2 such corners, whereas this image is the only image that includes 2 top left corners and 1 bottom right corner. These 2 images do not include any of these corners. The image classification will therefore rely on different local features that are identified in the image, and not on individual values in the pixels. If we would shift the digit in this image one step to the right, that should not affect the classification of this image, because the identified local features are still the same. By using a range of different filters, we can identify a large variety of local features in the images. This is one reason why we use several filters, because different filters will learn to identify different features. We will now have a look at the architecture of VGG16, which is a very deep network. The green boxes represent convolutional layers, whereas the blue boxes represent pooling layers, which make the matrices smaller. Max pooling is used in VGG16. After pooling the 64 feature maps, with a 2x2 pooling window and a stride length of 2, the size of the matrices will be reduced by 50%. The size of the final 512 matrices will be 7 by 7. If we flatten these 512 matrices, we'll get the one-dimensional array that is 25,088 long, which serves as an input to a fully connected layer. The output layer has 1000 nodes, because the network was trained on the ImageNet dataset, which has 1000 categories. VGG16 can take an image of any size, which is first normalized and rescaled to a size of 224 × 224. The network then applies a three-dimensional filter. This filter can be seen as a cube that contains 27 different weights. In addition to these weights, a bias weight is used. 64 of such filters are used in the first convolution, which results in 1792 weights to be optimized. Next, it uses a second convolution step on the 64 feature maps by using a filter with a depth of 64. 64 of these deep filters are used, which result in 36,928 weights. Note that no weights are used in the pooling step, which means that this layer is not trainable. Since this array is 25,088 long and is connected to 4,096 nodes, including a bias weight for every node, there will be about 102 million weights in this layer, 16 million in this layer, and about 4 million in the last layer. The network has therefore 16 trainable layers that include about 138 million weights to optimize. The ReLU activation function is used throughout the network, except for the output nodes that use the softmax function to compute the probability for the outcome classes. So, when VGG16 was trained on the ImageNet dataset, its 138 million weights were optimized to classify the 1000 different categories in the dataset. The first layers of the network have learned to identify basic edges, whereas the layers in the middle have learned to identify things like eyes, ears, and tails in images that include, for example, cats. Layers further down can be seen as they have been able to identify larger parts, like heads, whereas the final output nodes identify the object in the image. However, VGG16 was not trained to identify just a cat. It was actually trained to identify different types of cats that are included in the ImageNet dataset. This means that in 1 out of the 1000 output nodes, you will find the label tabby cat. If we would give the network an image of another type of cat that was not included in the ImageNet dataset, it would have problems predicting the image because it has not been trained on such a cat. I will now show how to use transfer learning, where we can, for example, use this part of the trained convolutional layers of VGG16 and delete this part of the network that includes the fully connected layers. The number of layers to remove is something that you need to explore to see if the network performs better or worse based on the validation dataset. We then add the following new layers to the network to predict just cats and dogs. Note that we here include all types of cats and dogs, not just the types VGG16 has been trained on. This is a so-called global average pooling layer, which creates a one-dimensional array with the average values from the 512 matrices. Then we connect 64 nodes to this array, which will result in 32,832 weights to be optimized. Finally, we add just one output node that computes the probability that it is a dog. If this probability is greater than 0.5, the network predicts that the image contains a dog. And if it is less than 0.5, the network predicts that the image contains a cat. This will give us a network with 32,897 trainable weights and about 14.7 million non-trainable weights. This is the main idea with transfer learning, because we freeze these weights that were optimized once the network was trained on the ImageNet dataset, and modify the network by adding new layers with trainable weights to train the network on a new task. I will now show a tutorial on transfer learning that you can try in Python. We first need a dataset to train on. I will here use the following dataset with cats and dogs. Click here to download the files. After you have unzipped the file, you should see the following folders. I've here saved these two folders in the following path. The test folder includes about 2000 images of cats and dogs, whereas the training folder contains 8000 images. Let's create a new folder that we call validation set, so that we also have validation data during the training. Inside this folder, we create two new empty folders with the names cats and dogs. These folders must have the exact same names as the subfolders in the test and training data folders. To show the power of transfer learning and to reduce the time for training, we keep only the first 300 images in these two folders and move the 700 images starting with the file name 301 and ending with the file name 1000 to the empty folders in the validation set. This means that we will delete the remaining 6000 images of cats and dogs that we downloaded. If you have fewer images to train on, it is enough to have, say, 200 images in the validation data. The reason why I have used 1400 images in the validation data is just to get an accurate estimate of the performance of the networks for this video. So there should be 2000 images in the test dataset, 600 images in the training dataset, and 1400 images in the validation dataset. If you see files that end with the following characters, it means that there are some duplicates. If you like, you can remove all these files from the corresponding folders. Let's first see how we can use VGG16 for prediction. We therefore input VGG16 and its associated functions. Then we define the path to the image that we like VGG16 to classify. I've here used the file cat3, which can be found in the folder training set. Note that you need to change the path to where you have saved your images. This line loads the image and resizes it to 224 × 224, which is the required input size of VGG16. Next, the image is turned into a NumPy array with the following shape. And a batch dimension is added because VGG16 expects a batch of images. Next, we normalize the pixel values to match what VGG16 expects, which is centered pixel values around 0. Then we load VGG16 and its weights that were optimized based on the ImageNet dataset. Note that VGG16 will be downloaded the first time you run this code. Next, we use the network to predict, which will result in 1000 probability values because there are 1000 output nodes in the network. We then convert the output probabilities into labels with the top 10 highest probabilities and print these. We can also show the image of the cat. VGG16 predicts that it is a Siamese cat with 31% probability. This is actually incorrect, because this is not a Siamese cat. Due to its large ears, VGG16 is close to predicting it as a wallaby, a hare, or a rabbit. Remember that VGG16 has not been trained on this type of cat. which explains its uncertainty. Once you get the idea of how to use one network, it is very simple to use another pre-trained network. I will here use the MobileNet, which is a much smaller network compared to VGG16. To use this network, we only need to change in these two lines from VGG16 to MobileNet. Similar to VGG16, MobileNet has not been trained on this type of cat, which explains its uncertainty. I will now show a simple Python code to perform transfer learning with a range of different pre-trained networks to predict cats and dogs. We will start with VGG16. We begin by importing the following classes and functions in VGG16. Then we set the required image size for VGG16. This means that our images with cats and dogs will be set to a size of 224 × 224 pixels when they are plugged into VGG16. We here specify the batch size that we like to use. A batch size of 32 means that during each training iteration, the network processes only 32 images at once before updating the weights of the network. This parameter can be set to determine how many layers of VGG16 that we like to train. I've here set it to 0 because we will in this example not train VGG16. This means that we will freeze the values of the weights. Next we enter the paths to the folders where we have the images for training, validation and testing. This code assumes that the folders contain subfolders with the names of each class. In our case, the subfolders should have the names cats and dogs. This code specifies how the images will be pre-processed. For the test dataset and the validation data, we use the same normalization as VGG used on the images in the ImageNet dataset. For the training data, we will also perform data augmentation, which is a great way to generate more variation of the images and to reduce the risk of overfitting when we have few images. This is an example image in the training data. With this parameter, the image will be randomly rotated by up to 20 degrees in each direction. This parameter controls the shift range, where 0.2 means that the image can be randomly shifted up to 20% to the left or right. Note that the addition of the new area in the image is by default filled in with the nearest pixel values. This parameter controls how much we should randomly zoom in or out. And by setting this parameter to true, we can even flip the image. By combining these parameters with random values within the specified ranges, we might end up with the following image for the network to be trained on. For example, the network might see this image in the first epoch, then this image during the second epoch, and this in the third epoch, and so forth. Next, we load and preprocess the images. For images in the training data and the validation data, we randomly shuffle the order of the images in each epoch. However, this is usually not done for the test data because the predictions made by the network should correspond to the original order of the test images. If you have more than 2 outcome classes, you should change from binary to sparse. Next, we load VGG16 and use its weights that were optimized based on the ImageNet dataset. If we set this parameter to false, it means that we only keep this part of the network. When you run this code for the first time, the network without the top and with the given input shape will be downloaded. When we run this line, we will see all the layers of VGG16 that we will keep for our own network. Note that we freeze all the weights of this network, which means that they will not be trainable. This piece of code simply makes sure that none of the layers are trainable. This code can be used if we would like to train some of the layers towards the end of the network. For example, if we would set this parameter to 2 at the beginning of the code and run the complete code from the beginning, we will see that this layer is now trainable because we now have 2.36 million trainable weights. How many layers you should freeze or unfreeze is something that you need to explore. Anyway, in this example, we set this parameter to 0, which means that we freeze all the weights. Next, we build our model by using the function sequential, where the base model is this part of VGG16. To create a long one-dimensional array of all the values in the 512 matrices at the end of VGG16, we compute the average value of these matrices by using global average pooling. Then we add a fully connected layer, where the ReLU function is used as the activation function in these nodes. Since we have a binary outcome, cats and dogs, we use just one output node with the sigmoid activation function. If you have more than 2 categories, for example 3, you enter the number of categories and use instead the softmax function. If we now run the model.summary function, we can see that we have 2 trainable layers, including a total of 32,897 trainable weights. Finally, we compile the model and specify that we would like to use a learning rate of 0.001, a loss function based on a binary outcome, and that we like to display the accuracy during the training. If you have more than 2 outcomes, you should change from binary cross-entropy to sparse categorical cross-entropy. If we run this code, we will start training the network. Since we have a batch size of 32 and 600 images in our training data, we will run 19 batches or iterations in each epoch. After the first epoch, in which the network has seen all the images, the accuracy of the validation dataset will be computed, which will take a few minutes because we have 1400 images in the validation dataset. I here use only 5 epochs, because the validation accuracy stops increasing after 5 epochs. Training the network as long as the validation accuracy increases is called early stopping, which makes sure that we stop training when the network starts to overfit. Watch the following video to understand how early stopping prevents overfitting. Finally, we evaluate how well the network can predict the images in the test data. We see that we get a test accuracy of about 97%. Note that the accuracy will vary between the runs, because the training involves many random components, such as augmentation, random initial values of the trainable weights, and the random order of the images during the training. This is the computational power of my laptop that I used to train the network, which worked fine for this simple example. However, to speed up the training time, one should instead use a computer with a powerful GPU, which you find in today's gaming computers. Let's also try MobileNet to see if it performs better. This is the complete code that we have used with VGG16. To instead use MobileNet, we only need to make these changes. You can find this code on my homepage. Note that the training now goes much faster because MobileNet is a much smaller network than VGG16. By using MobileNet as the base model, I got a bit higher accuracy than VGG16 based on the test dataset. This column shows the size of the top of the network that we use as the base model. Let's try a few other networks. By using ResNet 50, I got an accuracy of about 98%. And with ResNet Mobile, which is a small network, I got a bit higher accuracy. By using EfficientNet B0, which is also a small network, I got an accuracy of 98.5%. With EfficientNet B7, which is the largest network in the EfficientNet family, I got an accuracy of 99.7%. However, since this network is very large and processes images of a larger size, it took several hours to train the network on my laptop. Since the image size is now larger, TensorFlow tries to allocate more memory, which might slow down the training. One can then try to reduce the batch size. The new version of EfficientNet, the one with medium size, is a lot faster. It took about 25 minutes to train and validate on my laptop, and resulted in an accuracy of about 99.4%. Once we have decided which network to use for future predictions, we should save it. I will here save the network that was based on MobileNet. After you have trained your network, you simply run the following line, which will save the network in your current working directory with the following file name. The size of this file should be around 13 megabytes. To use our saved network, we need to import the following to preprocess the image according to the requirements by the input of MobileNet. Then we load our saved network. As an example, I will here try it on the following cat image in the test dataset. The image is here preprocessed and then predicted by the network. The output probability corresponds to the probability that it is a dog. To print the probability that it is a cat, we therefore take 1 minus the probability that it is a dog. The network predicts that it is a cat with a probability of 93%. Finally, let me illustrate the power of transfer learning. For example, I will here use VGG16 as the base model, starting with random weights. By changing this line from false to true and running the complete code, this will result in that all layers and weights are now trainable, which means that we no longer use transfer learning because we will train the network from scratch. If you now run the code, you will notice that the training takes a lot longer time and that the network has not learned anything during the first 5 epochs because the accuracy is only 50%, which is not better than chance. This clearly shows the power of transfer learning when we have few images to train on. This was the end of this basic video about transfer learning. Leave a comment below with changes in the code if you manage to get a higher accuracy than 99.7%. Thanks for watching.